Welcome to our series of videos focusing on interdisciplinary socio-environmental team synthesis. I'm Margaret Palmer, professor at the University of Maryland and director of SSYNC, the National Socio-Environmental Synthesis Center. These videos were designed as a tool to help understand and hopefully solve socio-environmental problems. After all, environmental problems are by definition social problems. The first video in this three-part series presents examples of how researchers use a socio-environmental lens to study environmental problems. Some of the key characteristics of socio-environmental systems that make their study challenging are highlighted in the video. The second video provides an overview of the synthesis research process as well as the concepts and approaches used by synthesis teams, particularly those teams that are highly interdisciplinary. Finally, the third video in the series presents common approaches and methods that are used to harmonize the diverse data needed for socio-environmental synthesis.
In this video, we will introduce and provide examples of socio-environmental systems as complex dynamical systems, characterized by nonlinear interactions and feedback loops both within and between the social and ecological subsystems. Throughout the video, we will focus in particular on feedbacks because they can lead to unexpected and sometimes dramatic social and environmental outcomes. Because both human and ecological systems often change or adapt based on experience and outcomes, they are more correctly called complex adaptive systems. To begin this first video, we highlight an interesting study that illustrates the complexity of coupled human-natural systems and how research can clarify the factors and relationships influencing their characteristics and changes in them over time. Our first example of understanding environmental problems through a socio-environmental lens is the cod fishery case in the Baltic Sea, that industry's prosperity and subsequent depression. We will also look at the role of social dynamics as opposed to traditional ecological studies to bring the socio-environmental view into focus. In the 1980s, following a period of extremely high abundance, the cod fishery in the Baltic Sea, a water body in northern Europe, suddenly collapsed due to a combination of overfishing and poor environmental conditions. Interestingly, with the crash of the cod fishery, one of its important prey items, a fish about 12 centimeters long called sprat, increased dramatically. Changes in zooplankton prey and other fish, such as herring, also occurred. This presented an interesting system from a socio-environmental synthesis perspective, because rich biophysical data were combined with qualitative social information through a modeling tool called generalized modeling, which revealed insights into the collapse. This got a team of researchers led by Steve Lade and Maya Schluter interested in understanding the role of social ecological coupling in the Baltic cod fishery collapse. The project began when a team of Baltic Sea experts from the natural and social sciences worked together to develop a conceptual model of the key ecological and social factors that contributed to cod stock dynamics. This highly simplified diagram was later formalized into a dynamical systems model. The ecological dynamics during the cod boom and collapse had been well studied, and like the dynamics of many other ecological systems, a number of complex interactions between environmental conditions and food web dynamics were at play. Not surprisingly, the cod catch was influenced by total fishing efforts as well as cod abundance, and it was well known that cod catch had increased over time. Prior work by others using quantitative and qualitative approaches indicated that the pressure fishermen exerted on the cod fishery was influenced by the size of the Baltic Sea fishing fleet and the West Coast fleet, as well as the time they spent fishing. And their decisions about buying new boats or changing their fishing effort were influenced by psychological, economic, and institutional processes operating within a given social and biophysical context. Those included elements such as perceptions of profitability, subsidies local fishermen received from the government, and costs they had sunk into gear and boats. The team was able to include these factors in the model along with the interactions between the social and biophysical system using qualitative and quantitative data from other studies, as well as theoretical work on what factors influence behaviors. Steve, Maya, and their colleagues used a generalized modeling approach that did not require detailed information on the processes within the model, so they could test the relative importance of social and ecological processes for the stability of the cod fishery using a combination of qualitative and quantitative data. Ecological models alone may be able to reproduce the fishery dynamics, but cannot be used to investigate the processes driving catch-and effort, nor the social ecological feedbacks in which these processes participate, and which drive the social ecological system into a new state. By developing an empirically driven model that also was informed by rich sources of qualitative information and data, they were able to show that understanding a complex problem, such as collapse of a fishery, required incorporation of social dynamics.
So the basic concept is that people are influenced by the environment, and the environment also influences people, and there's a tight coupling and interlinking between the two systems, and we can't really understand environmental problems without understanding the social dimensions and vice versa.
As shown in the example of the Baltic cod fishery, research on socio-environmental systems, as well as most synthesis projects, begin with teams developing a conceptual model which reflects their understanding or hypothesis on how the system works. These can include: what are the key components? How are they linked? Are those linkages positive or negative? And what is the potential for feedbacks? David Gill, a former postdoc at SASINC, discusses why it was useful for his research team to develop a conceptual model for marine protected areas.
And so for us, the conceptual model was very useful at the beginning of the research process because one important step in the research was to bound the system and to get an understanding of, even though there are many interactions inside and outside of our marine protected area system, it's important to bound, to create boundaries, to develop the scope of the analysis in a realistic, practical and pragmatic way. And so we were able to use such conceptual diagrams to understand what are the social processes that we're going to look at in this study, what are the ecological processes that we can look at, and what are some processes that we can use in places where we can't get those data.
Let's now take a look at an example of a conceptual diagram or model. This from a team of researchers studying the Boston metro region led by Dr. Paige Warren of the University of Massachusetts at Amherst. The team hypothesized that a combination of historical and social processes led to land cover transformations that not only produce the current ecosystem states, but also the health and well-being outcomes of people living in the area. Their work found that potential trade-offs existed between biodiversity and social equity for some kinds of transformations, for example, small-scale greening, but also some potential feedbacks from small-scale greening toward greater engagement in greening. A final example is drawn from work by Elena Guimarães of the University of Évora. Guimarães has been studying the Guadiana estuary on the border between Portugal and Spain, where increased tourism provides economic benefits but also contributes to water quality problems. She and her colleagues explored the idea that the use of an eco-labeling approach, which was given the Blue Flag Award, would stimulate tourism, which, in turn, might increase willingness of the year-round residents to pay for increased wastewater treatment. As a note, the Blue Flag Award is given on a seasonal basis and only if the water quality meets certain standards. All of these examples, the cod fishery collapse, the Boston metro region, and the Portuguese estuary, illustrate properties that characterize socio-environmental systems as complex adaptive systems. A systems dynamics approach is often helpful to identify and articulate the environmental and social pressures outcomes, feedbacks, and mechanisms. Feedbacks are the most difficult part in studying socio-environmental systems. They are typically nonlinear, and for socio-environmental systems, they occur across different temporal and spatial scales. Some processes and feedbacks occur slowly, over decades or longer, while others happen very fast. The components of the system, often called agents, react to changes, but the overall behavior of the system emerges from the combined interactions and feedbacks. Rather than operating under central control, the system changes in response to interactions between all of the components and does so in ways that are very difficult to predict. So predictions of system state are probabilistic. Small events or changes in one component can result in large or sudden changes at the system level. But they are essential to focus on because they are most helpful in informing management. In our introduction, we touched on the concept of a feedback loop. Because they play critical roles in the dynamics of socio-environmental systems, we provide one final example from Indonesia. Villagers there were trapped in a cycle of poverty and natural resource degradation. Too many people migrating to one region, combined with expanding agriculture and timber markets that led to deforestation, strong feedbacks were set in motion that resulted in impoverishment and social decline. As population size in the village increased, the land available for farming decreased. The result? An increase in poverty as income from crops fell or disappeared. Increased poverty then led to fewer educational opportunities, which in turn impacted employment as fewer income-producing jobs were available that would have replaced jobs in farming opportunities. The consequence of all of these factors was increased poverty, which combined with the already scarce availability of land, led to increased forest clearing for agriculture. Illegal logging also showed an increase, as did the removal of wood for fuel. All of these elements resulted in further reduction in available forests, ultimately resulting in less water infiltration and soil moisture, which also reduced forest area, given the lack of support for seedlings to thrive and grow. The only way to reverse the social decline and loss of forests that are valued for carbon sequestration and biodiversity is to weaken or reverse some of the feedbacks, which can be accomplished through a number of social programs. Environmental problems are social problems, and the urgency to find solutions to improve the lives of people today and those in future generations has never been greater. As is evident in all of the examples presented in this video, there is a growing recognition of the need to better understand and manage natural resources to both meet human needs and sustain those natural resources. Viewing these as complex systems that include both social and environmental dynamics is essential, and has led to dramatic growth in research on socio-environmental systems. This first video in our three-part series focused on defining socio-environmental systems and some of their characteristics. These are adaptive systems characterized by nonlinear feedbacks within and between the social and environmental components. And these feedbacks often span different temporal and spatial scales. When there are many feedbacks, it can be quite difficult to predict the future status of the natural resources and of the social systems that are linked to those resources. Despite this, interdisciplinary teams are making great progress in overcoming these and other difficulties associated with understanding socio-environmental systems, and synthesis research is an important tool in this process.
The next video, which is the second in this series, focuses more closely on the synthesis process itself. The benefits and challenges are discussed along with strategies for enhancing interdisciplinary team progress.